Here's lesson number 2 in Unit 6. This is about the various methods that we use for rock classification. Recall from the previous lesson that there are 3 main types of rocks: igneous, sedimentary, and metamorphic. We're going to begin with a classification of igneous rocks. Remember that igneous rocks form either intrusively, this means plutonic or underground, or extrusively, which can be volcanic through eruptions. We classify igneous rocks based on their texture or crystal size and their composition, or what kind of minerals they're made out of. So let's begin by discussing igneous rock texture. The first texture we have is phaneritic. Phaneritic is coarse-grained with large visible crystals. The crystals formed during the cooling of the magma that created the igneous rock. So large crystals or coarse-grained texture indicates that that igneous rock cooled slowly, so it's more likely to be an intrusive igneous rock because the longer magma has to cool, the larger the crystals can grow. The 2 examples that I have here are granite, which is a common igneous rock that you've probably seen a lot, and another one is gabbro. You can see the large visible crystals on the face of this rock. The next texture is aphanitic, and aphanitic means fine-grained rock. These crystals are not visible to the naked eye. They're still there, you just can't see them without using some type of magnification device. So these small crystals indicate that this igneous rock is more likely to be extrusive because it would have hit the air and cooled very quickly, meaning the crystals didn't have time to grow very large. The examples we have here are rhyolite, which is like the fine-grained version of granite, and basalt, which is like the fine-grained version of gabbro from the previous slide. The third igneous texture is glassy. These are very shiny and smooth igneous rocks. These cooled immediately, so they had no time for crystals to grow. There's really no crystals present in these rocks. The example that I have here is obsidian. You're all familiar with obsidian. It's this really shiny, glassy looking rock. Typically it's black, but I just put this example in here to show that there can be color differences in obsidian. Our next igneous texture is vesicular. Vesicular igneous rocks have holes in them that were from tiny little gas bubbles that were present when that lava erupted. Examples that we have here are pumice. Pumice is a common rock. A lot of people will use this as some type of abrasive. Some people will use it to scrub the dead skin off of their feet. Another example is scoria. Scoria, you can see these big bubbles here. A lot of the scoria we have around Montana is either this black or this reddish color. A few more less common textures of igneous rocks. There's porphyritic, which means most of the rock has fine-grained texture, but there are some large crystals that are present. An example we have in this picture is a piece of porphyritic basalt, so it's a piece of basalt that just had some crystals that grew larger than others. Another texture is pyroclastic. Pyroclastic textured rocks are typically kind of dusty with some little chunks of ash present in them. The example picture I have here is a piece of volcanic tuff. And the final igneous texture is pegmatitic, and this texture is when there are some extremely large crystals present in the rock, much bigger than phaneritic crystals. These very large crystals indicated that the rock cooled extremely slowly, most likely very deep underground. The example I have here is a piece of felsic pegmatite. You can see these big pink and white crystals that are much bigger than the crystals that you would find in a normal piece of granite. Now let's discuss the various compositions of igneous rocks, so the types of minerals that they're made out of. First we have felsic igneous rocks. These are rocks that are high in that mineral silica. Remember we talked about silica when we were talking about the explosiveness of magma. The more silica present, the more explosive the magma is. Felsic igneous rocks are low in metals such as iron and magnesium. When you look at an igneous rock, you can tell its composition based on its color. If it's made of minerals that are mainly light colors like pink or tan, it's going to be a felsic composition igneous rock most of the time. The examples we have here are granite and rhyolite. These are made of very similar minerals. It's just that granite has a phaneritic texture and was able to cool slowly, versus rhyolite has an aphanitic texture and cooled much more rapidly. Our next composition is mafic. This is the exact opposite of felsic. So mafic igneous rocks are low in silica and high in metals such as iron and magnesium, and that gives them a dark color. Typically mafic igneous rocks are going to be black or gray in color. The examples we have here are gabbro and basalt. So again, gabbro, similar composition to basalt, but gabbro was able to cool slowly, so it had time to grow these larger crystals, versus basalt cooled much more quickly. The texture is very fine-grained. About halfway between felsic and mafic, we have a composition that we call intermediate or andesitic. This is about half felsic and half mafic mineral composition. So the examples we have here, this is a piece of diorite. This is a large-grained, coarse-grained Phaneritic igneous rock of intermediate composition. You can see there's about half as much white as there is black mineral in this rock. And then our other example is regular old andesite. Andesite has a more aphanitic texture, so you can't see the individual crystals like you can in this diorite. However, you can see that there's a speckling of light and darker colored minerals within this one rock, giving it an intermediate or andesitic composition. Our final igneous composition is called ultramafic, and these are igneous rocks that are very, very, very high in those metals like iron and magnesium, and that interestingly gives them a bright green color. The examples I have here are olivine, a more aphanitic texture, and pyritite, a more phaneritic texture with the bigger crystals. Now remember, just because these are lime green doesn't mean that this is a rock called limestone. That happens every year. People think that these bright green rocks are the limestone, and that's not the case at all. These are olivine and pyritite. Moving on to sedimentary rocks, let's review the formation processes for sedimentary rocks really quick. Remember, weathering and erosion, the processes associated with water, especially running water, wind, ice, especially glaciers, and then gravity break down rocks into sediment. Deposition is the process of those sediments then being dumped in layers somewhere, and lithification is the process of those sediments combining to form a new sedimentary rock from the pieces of old rock that were weathered and eroded and deposited. So compaction is when these sediments are compressed together by the weight of all of the sediment above them, because remember, deposition happens in layers, and then cementation occurs when certain types of minerals that are dissolved, especially in water, will be deposited in the pore space between those little chunks of sediment, and that cementation occurs when these minerals act sort of like a glue and hold those sediments together into a new rock. So the two main criteria that we use to classify sedimentary rocks are their texture and their parent material. So what kind of rock was weathered and eroded and deposited to form this new sedimentary rock? So our first texture of sedimentary rock that we'll discuss is clastic. This is the most commonly thought of texture of sedimentary rocks. These are formed from those little chunks of sediment that were weathered and eroded and deposited and then smushed together by compaction and cementation. So clastic sedimentary rocks will be rough to the touch, so feel kind of like sandpaper. The larger the grains are in that sedimentary rock, the rougher it will feel. So remember, sand is bigger than silt, which is bigger than clay. So a classic sedimentary rock made of sand particles is going to feel a lot scratchier than a classic sedimentary rock made of clay particles. Examples that we have here is one called breccia. Breccia has these large angular chunks of sediment that are glued together with mineral in between. Conglomerate is another type. It's very similar to breccia, except for the large sediments are more rounded, like little river pebbles that have been glued together through natural cementation processes. And then here's an example of a piece of red sandstone. It's red caused by there's iron present within this rock, and you can, if you look at it, you can see just how scratchy this would feel to the touch if you were to like rub your finger across this piece of sandstone. A second texture of sedimentary rocks is chemical. This is less commonly thought of, but chemical sedimentary rocks are made from minerals that were once dissolved in water and then get deposited, settle out of solution, and form a new rock. These are much smoother to the touch compared to a clastic sedimentary rock like on the previous slide. Examples that we have here are chert and rock salt. So here's a nice beautiful piece of pink Himalayan rock salt. So this was ancient ocean salt that was dissolved in ocean water a very long time ago and then was deposited and formed rock salt. This is an example of chert. This is a really smooth rock. You can find a ton of chert if you go out in the area of like Montana City. Chert is, you can see it fractures in this interesting way, which made chert a good material for Native Americans to use for arrowheads. So if you go walk around out in Montana City, there's a good chance that if you're just looking down at the ground, you can find some piece of chert that was either used as an arrowhead or as a piece that was broken off of an arrowhead that was being made. Our final sedimentary texture is biologic, and biologic sounds like biology, which is the study of life. And so biologic sedimentary textured rocks are made of things that used to be alive. They could have been plants or animals. Examples that we have here, here's a piece of bituminous coal. So coal is made out of ancient swampy plants that got buried and compressed over a very long period of time. And here is the limestone. See, it's not bright green. It's actually, this piece is kind of a whitish color, but limestone can come in other colors like gray or kind of brownish. and limestone is made of the ancient skeletons of tiny little sea creatures that died, and then their little skeletons sank to the bottom of the sea and formed a bunch of layers and got compressed and cemented together into limestone. Limestone is, you can do a test on limestone, you can drop a little bit of hydrochloric acid on it, the same acid that's in your stomach, and it will bubble because it's made out of a lot of calcium deposits. So it's the same as like if you've ever seen those experiments where they take a baby tooth and put it in a cup of Coca-Cola to watch it dissolve. It's the same kind of process. Teeth are high in calcium, so acid dissolves them. Limestone is high in calcium, so acid will dissolve it. So just a couple of features that could be present in sedimentary rocks and not in other rock types. You can tell the age of a sedimentary rock because the older layers are going to be towards the bottom of a column of rock versus the younger layers, just because of the way that gravity deposits them. The stuff that's at the bottom was deposited first compared to the stuff at the top. You can get some clues about ancient climates from sedimentary rocks. For example, ripple marks show the presence of water. So this is a picture that I took when I was hiking in Glacier Park last year, and you can see these ripple marks indicate that there was water present over the top of this rock in the past. Mud cracks are another example of ancient climate because you'll get these formations typically in like a desert where there was water and then it dried up really fast. It leaves these crack formations, and those can solidify into solid rock to give us clues about ancient deserts. And fossils are going to be present in sedimentary rocks. They won't be present in igneous rocks because remember that's cooled magma, so if there was any kind of fossil it definitely melted. And metamorphic rocks, there's such heat and pressure involved with metamorphic rocks that the fossils are going to be squished and unrecognizable. So fossils are the remains of dead organisms that you can find in sedimentary rocks. Here's another piece of limestone. It's got that whitish color. This is called fossiliferous limestone because there's large distinct chunks of fossils of sea creatures that are present in here. So like here you can see a big old seashell fossil present in this chunk of limestone. Moving on to our final rock type, the metamorphic rock. Metamorphic rock, remember, are formed on existing rocks when heat and pressure act on them to partially melt them and change their structure and composition. So again, the way that we classify metamorphic rocks is based on their formation, how did they form, what kind of heat and pressure were associated, and then also certain textures characteristic of metamorphic rocks. So the formation of metamorphic rocks can happen in two ways. The first way is contact metamorphism. So this is when magma gets into some rock bed, partially melts the rock that it's touching, and then that rock recrystallizes into a new metamorphic rock. This is called low-grade metamorphism because it's not a humongous change that occurs to the parent rock material when the magma melts it. An example that we have is when magma gets into a bed of limestone, it will melt that limestone and turn it into marble. So here's an example. You can see a piece of limestone that has a big seashell fossil in it like this. When it gets melted by magma to turn into marble, there's no evidence of that seashell fossil in the marble anymore. The second way that metamorphic rocks can form is through a process called regional metamorphism. Now, regional metamorphism takes place over a much larger area than contact metamorphism because regional metamorphism is associated with plate boundary interactions. So plate tectonics, the plates moving together, can generate heat and pressure that can cause significant changes to the rock. And so this is called high-grade metamorphism because there is so much more change that occurs between a parent rock material and the rock that forms after metamorphosis from the heat and pressure associated with plate boundary interactions. So an example that we have here is shale, a sedimentary rock. Some heat and pressure applied will turn that shale into slate, which is harder and has some layers to it. More heat and pressure will turn slate into phyllite, which starts to change the mineral composition a little bit. Phyllite with more heat and pressure will turn into schist, and schist with more heat and pressure will turn into a high-grade metamorphic rock called gneiss. There are two types of textures that we use to classify metamorphic rocks. The first is called foliated texture. Now, foliation refers to any layering or folding or striped kind of patterns that form in metamorphic rocks because of the pressure associated with the squishing of the rocks. So two examples we have here are gneiss. This is a picture of gneiss. A lot of times kids will call this zebra rock because it has black and white stripes and looks kind of like a zebra. And here is a picture of slate. So remember in the previous slide, shale with heat and pressure applied to it will turn into slate. And so you can see that these are foliations here. They're not foliations by color like in gneiss, but you can see that there are indeed layers in this piece of slate. The second type of metamorphic texture is called non-foliated, so this just means that they're metamorphic rocks that don't have those layers or bands that are characteristic of metamorphic rocks. So examples of those are marble. Remember, marble forms from contact metamorphism. When magma gets into limestone and melts it, it recrystallizes into marble. Here's an example of quartzite. Quartzite is a really common rock. When you take something like sandstone and apply heat and pressure to it, it will recrystallize into quartzite. And then here's an example of anthracite coal. So bituminous coal was a sedimentary rock, and if you apply heat and pressure to the bituminous coal, it will become anthracite coal, which is a high-grade metamorphic rock. Anthracite coal, because it's compressed, has much more energy burning capacity in it when compared to bituminous coal.